Hello everyone, I'm Mr. Pinola. Today on your screen, you're viewing a virtual simulation that is very similar to the lab that we did in our last video together. Here in the simulation, we have a container of water and a container of olive oil. There are roughly equal amounts of water and olive oil, and they are both sitting above two heaters. I've linked the heaters to make sure that both the water and the olive oil receive the same amount of energy being transferred to them in the form of heat. Remember, heat always flows from high to low temperature, and that's what's going to be happening here. I'll turn on the heaters, and the heat will transfer from the heater to the substance, either to the water or to the olive oil. Do you remember which substance, water or olive oil, will change its temperature more dramatically? Well, I might be a small part of your screen right now, but if you can look behind me, you'll see two numbers for the specific heat capacity of both water and olive oil. Water's specific heat capacity is 4.81 joules per gram times degrees Celsius. Olive oil's specific heat capacity is 1.917 joules per gram times degrees Celsius. Notice that olive oil's specific heat capacity is much lower than water's. That means that olive oil will change its temperature more dramatically when it is exposed to the same amount of heat. Let's have a watch in our simulation and verify that that's true. 3, 2, 1. As you can clearly see, the temperature of the olive oil has changed very dramatically, and the temperature of the water, well, it has gone up. But due to water's higher specific heat capacity, it is not as dramatic a change as the change in temperature of the olive oil. So now let's take a look at a slightly different example. We have two other objects, iron and brick. Can you guess which object will change its temperature by more? Well, the problem is I haven't really told you about the specific heat capacity of the iron nor the brick. However, it might be helpful to know this. Brick has a lower specific heat capacity than iron. What does that tell us about how their temperatures will change when I expose them to heat? Well, since brick has a lower specific heat capacity, chances are its temperature will change much more easily. Remember, temperature, or more specifically temperature change, and specific heat capacity have an inverse relationship. If an object has a very high specific heat capacity, like water, its temperature will not change very easily. However, if an object has a very low specific heat capacity, like oil, its temperature will change very dramatically. We just said that brick has a lower specific heat capacity than iron. That means brick should change its temperature much more dramatically than the iron. Let's have a watch in 3, 2, 1. Notice the temperature of the brick is rising, as is the temperature of the iron. But the temperature of the brick has gone up by a little bit more than the temperature of the iron. That's because brick had a lower specific heat capacity, and therefore it was a lot easier to change the temperature of the brick. Hopefully now you very clearly see that a lower specific heat capacity will yield a bigger change in temperature. Oil had a lower specific heat capacity than water, just like brick had a lower specific heat capacity than iron. And as a result, the oil changed its temperature much more dramatically than the water, and the brick changed its temperature much more dramatically than the iron. Maybe you've noticed this before. Look at the difference between water and oil. Have you ever tried to boil water in order to make pasta at home? Maybe you have. And maybe you've noticed that that water takes a really, really long time to boil. Water has a higher specific heat capacity than almost any other material that we can think of. And as a result, it takes a lot of energy, and it is very hard to change the temperature of water. And that is thanks to water's really high specific heat capacity. So that's great. We know that objects that have high specific heat capacities need a lot of energy to change their temperature, but objects with low specific heat capacities will change their temperatures very dramatically. But what can we learn from specific heat capacity? Well, you might remember that specific heat capacity had a symbol that we can use to represent it in an equation. Specific heat capacity was represented by the symbol C, a lowercase c. You can think about the word capacity as being responsible for that symbol. We also noticed that there were two other factors that affected how something changed its temperature. One of those other factors was heat. If an object was exposed to a lot of heat, then it would change its temperature by a big amount. If an object was exposed to very little heat, then it would change its temperature by a small amount. Heat was given the symbol capital Q. Lastly, there was one other factor that we realized affected how much an object changed its temperature by. And that was mass, denoted by the symbol lowercase m. Objects with very small masses, like little puddles, change their temperature by a large amount. But objects with a lot of mass, such as an ocean, for instance, would take a very long time and not change its temperature by very much. These three factors together affect how the temperature of an object changes. But remember some of those words that we use to describe the relationship between two things? Those words inverse and direct? Well, we're going to look to see how each of these three factors affects delta T, or change in temperature. We already concluded that specific heat capacity has an inverse relationship with temperature change. And that's because as specific heat capacity went up, temperature change was not as big. What about heat? Heat would have a direct relationship with temperature change. As an object was exposed to more heat, or in other words, more energy was transferred to it, it changed its temperature by a larger amount. That's a direct relationship. More heat, more temperature change. And how about mass? Well, objects with small masses would change their temperatures by big amounts. That tells me that mass has an inverse relationship with temperature change. The smaller the mass, the bigger the temperature change. That's inverse. So now let's put our mathematician hat on for a second. We're going to see if we can come up with an equation to help us figure out exactly how the temperature of an object is going to change. And we're going to be doing that by setting up a fraction. Anything that goes in the top part of this fraction will have a direct relationship with temperature change. And that's because if the numerator or the top part of a fraction goes up, then the answer will go up as well. So numbers in the numerator, if they go up, they will create a bigger answer, a direct relationship. Factors that we put in the bottom of our fraction will have inverse relationships with the answer. That's because if the denominator of a fraction goes up, the answer actually goes down. Just like 1/4 is a smaller value than 1/2. If the number on the bottom is bigger, the answer is smaller. That's inverse. So now let's take our three factors that affected temperature change below and see if we can put them into this equation. Only one of these factors has a direct relationship with temperature change. That's heat, or Q. Two factors had an inverse relationship. So let's put them both in the bottom part of our fraction. That's mass, M, and specific heat capacity, C. Notice by following these rules, we've created an equation. Delta T equals Q divided by MC. The factors that are inverse relationships are on the bottom, and the factor that has a direct relationship is on the top. Now, there's one thing I don't really like about this equation that we have up here, and that's the fact that it's a fraction. I don't really like fractions when dealing with mathematics, so I'm going to eliminate the fraction. Do you know how to eliminate a fraction in a mathematical equation? If you said multiply by the denominator, you'd be right. So let's do that. We're going to multiply this fraction by MC. We're going to multiply by the denominator so that it cancels out. And we're going to do the same thing on the left side. Now let's write our new equation. MC times delta T is equal to Q. Guess what? This is the equation that your textbook and your equation sheet will use. In fact, a lot of people will even switch it around. It has the same meaning and write Q equals MC delta T because it flows off the tongue very easily. Q equals MC delta T. If you know the amount of heat that something provides, you know the mass of an object, and you know its specific heat capacity, you can figure out how much it changes its temperature by. And it all comes from this original equation in the blue, which we reasoned through together. So now let's use the equation we just spoke about, the equation Q equals MC delta T, to do a calculation. Let's say that I have a container of water. And let's say that container of water has a mass of 50 grams, or 50 G. And I place that container on top of a fire. And I leave it in the fire so that the fire transfers heat to the water. Let's say the fire transfers 2,000 joules. Joules because heat is a form of energy that's being transferred. 2,000 joules of heat from the fire to the water. How much will the water change its temperature by? Well, let's go to our board and do a calculation. We're going to, in step one of our calculation, collect our given information. First, we were told the mass of the water, which was 50 grams. So I'll write M equals 50 G. It might be weird to you that we're using grams and grams is not the SI unit, but in this case, we're okay using grams. I'll show you why in a second. Next, we're going to write in the amount of heat, Q. In this case, Q equals 2,000 joules of heat. That's because the fire gave 2,000 joules of heat energy to the water. Remember, just like always, heat flows from high to low temperature. Lastly, we know that our substance is water. That's the substance we're trying to find the temperature change of. And water, if you remember, has a specific heat capacity of 4.184. Now, the units are a little weird. The units are joules per gram times degrees Celsius. But now it might make sense why we're okay using grams. Since our specific heat capacity had a value in joules per grams times degrees Celsius, we are okay using grams up here because it appears in this unit as well. Lastly, we're asked to find temperature change. And can you guess what unit our temperature change is going to be in? If you said degrees Celsius, you'd be right. That's because degrees Celsius was also in the units for a specific heat, which means that it will give us an answer in degrees Celsius. So let's continue now with our math. We already have our equation in place, Q equals mc delta T, or the equation that we just derived a little while ago. But I can't leave this equation the way it is. That's because I want delta T, or change in temperature, and it's not by itself. It isn't isolated yet. I need to get it by itself. Right now, delta T is connected by mc through multiplication. So I need to divide, which is the opposite of multiplication, everything else that isn't delta T from the right side. So I'll divide by mc on the right. That will cause the m's to cancel and the c's to cancel, which is great. We just have delta T on its own now. But remember, what I do to one side, I have to do to the other. So I'm going to divide the Q by mc as well. Let's now rewrite what I have. Q divided by mc equals delta T. That should look familiar to you. That's the equation that we started with. The direct relationships on the top and the inverse relationships with change in temperature on the bottom. But we just showed how we can get that equation back from the original one. This is what we will use to calculate change in temperature because it has change in temperature, or delta T, isolated, or in other words, by itself. So let's finish out our math by doing a calculation here. We're going to plug into the equation we just got. Delta T is equal to Q, which is 2,000 joules, divided by M, which is 50 grams, times C, which is the specific heat capacity of water, 4.814 joules per gram times degrees Celsius. And I may have misspoke, it's 4.184, as you can clearly see. So now I've got to be very careful when doing my math. If I just plug these numbers right into my calculator, I'm not going to get the correct answer because the calculator doesn't know how to do PEMDAS, or order of operations. To make sure I don't make a mistake, I'm going to do all the math in the numerator of the fraction first, then all of the math in the denominator of the fraction, and then I will divide those two. So let's see what we get. On the top, it's still 2,000 joules. And on the bottom, it's 50 times 4.184. That gives me 209.2 on the bottom. But notice the grams over grams cancels, so I just have joules over degrees Celsius on the bottom. Now I can divide these two, 2,000 divided by 209.2, and I get a final answer of a temperature change of 9.56. And remember our units, degrees Celsius. If I give 2,000 joules of heat to a 50-gram container of water that has this specific heat, it will raise its temperature, or its temperature will change by 9.56 degrees Celsius. So as you can see, Q equals mc delta T is a very valuable equation. We can use it to find the amount of heat that you need to give to something. We can use it to find the mass of an object if we know everything else. We could also use it to find what the object is. Maybe we can identify the object by knowing about its specific heat capacity. And lastly, as we just showed, we can find out by how much its temperature will change. It's also very easy to reorganize because if you want mass, then you have to divide by C delta T. Divide out the rest. If you want to solve for specific heat, then you have to divide by M delta T. Divide out the rest. If you want to solve for change in temperature like I just did, you will divide by MC. Very easy to reorganize this equation. Lastly, if you wanted to solve for the heat that you need to give to something, the equation is already set up for you. Just keep in mind your units. So before I go, let's do what I just ended with. Let's keep in mind our units. Q is measured in joules because this is heat, and heat is a form of energy. Mass is actually measured in grams, not kilograms. But that's because the unit for specific heat capacity is joules per gram times degrees Celsius. Since we have grams here, we can have grams here. And that means that delta T will be measured in degrees Celsius because that's the unit that appears in the unit for specific heat capacity. I hope you're able to use this equation now, and good luck using it with the three-step method. Thanks for watching.